Okay, so this problem involves Ampere's law, which says that the line integral or path integral of B, let's ignore that. The path integral of B dot ds, that means the integral of the magnetic field B along the path ds is equal to mu naught I. I should also note that part of Ampere's law says that this path integral must be performed along a closed loop. So for the first part of the problem, we're given the radius of this wire, we're given the current through the wire, and we want to find the magnetic field at some point. First, let's find some point P where R is greater than the radius of the wire. So you're out here somewhere on the wire, and you want to find the magnetic field right there. Well, this, okay, so I'm going to draw the wire again, R. This holds true no matter what shape you draw. I can draw it, I probably shouldn't loop over myself there, but I can draw whatever shape I want, and as long as I perform this integral, this will hold true. But it makes no darn sense whatsoever to draw a weird shape like this because you're trying to take advantage of symmetry. This is very analogous to Gauss's law. What kind of symmetry are we taking advantage of? Well, if I draw the wire again, and let's say I use cylindrical symmetry, because remember this is a 2D projection of a three-dimensional thing. But anyways, it's 2D symmetry. At any point P, the magnetic field is going to be in this direction, right? Because we know this already, that the magnetic field circles around the current. So as I move all along this path, at any point in this path, the direction of ds, you know, the little segment of the line moving in the direction of the, as we move around that closed loop, is always going to be in the direction of B. And B will be constant at every point along that circle. We know that already from what we talked about, the empirical results of the measurements that Biot and Savart did, and they came up with the Biot-Savart's law, and they found that the magnetic field dropped off in magnitude with 1 over r squared as you got away. We know already that at any fixed distance away from the wire, the magnetic field is going to be constant. So that is why we draw this symmetric thing, the symmetric Amperian surface, if you want to call it that. So that means since B is constant all along the closed loop, we can pull B out of the integral. And we also know if we integrate around that closed loop, B is just 2 pi r. Because remember, we're not talking about the area here. It's not dA, it's ds. We're integrating the path. We're integrating the path along this circular route. So that is the circumference of the circle, and that just equals mu naught I. And I should say I enclosed, just to indicate that it's the, or it's not really enclosed. It's the current passing through this loop. I don't like to use the phrase enclosed because that works with Gauss's law, because Gauss's law has a Gaussian surface, so the charge actually is enclosed. In this case, the current is just passing through. Maybe I should say through. So that means the magnetic field at any point r, where r is greater than the radius of the wire, is going to be mu naught I through over 2 pi r. Well, that's just as expected, because we already found the same result with the Biot-Savart law. The difference is that Biot-Savart's law was really complicated. If you remember, we had to find at some point P, we had to integrate ds, you know, theta 1 to theta 2. We had to integrate all along that line. It was a really complicated result with the Biot-Savart's law. That's because this is a brute force method of calculating the magnetic field. This is a trick that makes things a lot easier. Okay, so let's now go down to the next part, which is find B at R is less than the radius of the wire. What that means is R is inside the wire, because yes, there's going to be magnetic fields inside of a wire. This gets a little more complicated. We go back to Ampere's law, B dot ds equals mu naught I through. Just like before, it's going to be constant all around, so we can say B times 2 pi r because of the symmetry, right? If the current density is uniform, let's assume uniform current density. So then we can say exactly like we did here, B times 2 pi r equals mu naught I through. But what actually is the current running through there? Well, we know that let's say we take a ratio of I at R over the total current, and I'll call that I sub big R, because big R is the radius of the wire. Well, we know that's going to be proportional to the area because we're assuming uniform current density. So the area of that this current passes through is pi r squared, and the area that this passes through is pi capital R squared, because this is the whole cross-sectional area of the wire. So that means I through, that I'm calling it, is equal to IR, because that's going to be the current through this Amperian loop is going to equal the current IR, which is equal to, cancel out the pi's, r squared over capital R squared IR, where IR is just this current we're given in the beginning, the total current through the wire. So then I can say B is equal to mu naught I through over 2 pi r, which is equal to mu naught over 2 pi r times I through, which is r over r squared. I just rearranged that. Times the total current, I sub big R, I'll just call it I, because that's what we're given and asked for in the problem. Okay, so I can simplify some stuff. B is equal to mu naught I over 2 pi r squared times r. So if we graph it, B as a function of r, well, r at 0 is going to increase up to the point where r equals r, the radius of the wire, and then it's going to decrease proportional to 1 over r, and this is proportional to r. So it increases linearly, and then it decreases at the rate of 1 over r once you get inside wire outside.